In this question, a scientist wants to determine the equilibrium constant K for the following fictional reaction at 367 Kelvin. So we've got 2D solid plus 3L2 gas gives 2DL3 solid. We're given 3 step reactions. Our goal is to figure out how are those step reactions going to combine to give us our goal reaction. Then we're going to be using that to figure out the equilibrium constant of our goal reaction. So this skill works exactly the same as the previous skill. The only difference is that we have slightly more complicated reactions that may have 3 or more steps. Let's start by writing down our reactants and products. So in the reactants we have D and L2, and in the products we have DL3. So for reactants, we have D. We should make note of the state as well. And we have L2, gas. And for products, we have DL3, solid. Okay, so we're going to look in each of our equations and figure out which of our goal reactants and products appear in those equations, because we need the goal reactants to be on the reactant side and the goal products to be on the product side. That will help us decide which direction do we need each of these reaction steps to be in. So let's start with reaction 1. L2 is the only thing in that reaction that appears in our goal reaction. L2 is in our reactants of our goal reaction, but it's in our products of this reaction. So that means I'm going to need this reaction to be backwards in order for L2 to be in the reactants. So we're going to need this to be backwards. We can write that equation down backwards. A2 gas plus L2 gas gives 2Al gas. In step 2, we've got D, which appears in our goal reaction in our reactants, and we've got DL3, which appears in our goal reaction in our products. So D is in the reactants of the goal reaction and this step, and DL3 is in the products of the reaction and this step. So that looks like it's already in the correct direction. So we want that to be forwards. So we can go ahead and write out this equation in the same direction it already is. We've got 2D solid plus 6Al aqueous goes to 2DL3 solid plus 3A2 gas. Okay, now for our last step, we've got Al gas goes to Al aqueous. Neither of those things appear in our goal equation here. However, let's look at our steps over here. We've got Al gas in the products of reaction 1 and Al aqueous in the reactants of reaction 1. So right now that means step 1 forms Al gas. Step 2 then uses up Al aqueous. So we're going to need to turn Al gas into Al aqueous so that it can get used up in that second step. So we're going to want to have gas on the left and aqueous on the right. We already have gas on the left and aqueous on the right. So this one is already in the correct direction, forwards. So I'm going to write out that equation now. We have Al gas goes to Al aqueous. Notice as well that now, because Al gas is on the left here and on the right here, when we add those together, those are going to be able to cancel out. And that's the same for Al aqueous here and Al aqueous here. When we add them together, those are going to be able to cancel out, which is what we want because Al doesn't appear in our goal reaction. So that's going to have to cancel out eventually. Okay, so our next step is figuring out how many moles of each reaction we need to add up to give our goal reaction. So in reaction step 1, we've got L2 in our reactants. That's the only place L2 appears in any of our steps. And we know from our reaction up here, we need 3 L2. So we know we're going to need 3 of step 1 in order to have enough L2 in our reactants. For step 2, we've got 2D in our reactants and 2DL3 in our products. Looking at our equation up here, we've got 2D in our reactants and 2DL3 in our products. So we already have the right amount of D and DL3. So that one's just going to be multiplied by 1. Now for reaction 3, Al doesn't appear in our reactants or products in our reaction, but we need it to cancel out overall with the other Als in our steps so that it doesn't appear in our goal reaction. So we know that in step 1, we've got 2Al gas, but it's multiplied by 3. So we've got 6Al gas total in step 1. In step 2, we've got 6Al aqueous times 1. So 6Al aqueous in step 2. That means we're going to need 6 of step 3 so that when we add these steps together, those Als are going to cancel. So we need 6 of that last step. Awesome. Okay, so we figured out the directions and moles required. Let's go ahead and add these equations up just to check it gets us to our goal reaction. So for step 1, we've got 3 sets of A2. Plus 3 sets of L2 gas. And that gives 3 sets of 2Al gas. So 6Al gas. In step 2, we've just got 1 set of that. So we've got 2D solid and 6Al aqueous in our reactants. And in our products, we've got 2DL3 solid and 3A2 gas. Finally, we've got 6 sets of equation 3. So we've got 6Al gas in our reactants, and we've got 6Al aqueous in our products. Now we need to see if there's anything we can cancel. So we can see we've got 6Al gas in both the reactants and the products, so that is going to cancel out. We've also got 6Al aqueous in both the reactants and the products, so that's going to cancel out. We've also got 3A2 gas in both the reactants and the products, so that's going to cancel out. So we're left with 2D solid plus 3L2 gas goes to 2DL3 solid. And that matches perfectly with our goal equation. So there is our goal equation. So adding all the steps up like that is a way of checking to make sure that we got the moles and direction for each reaction step correct. Lastly, we're asked what is the equilibrium constant K for this reaction at 367 Kelvin. So this is where we're going to be combining the equilibrium constants for steps 1, 2, and 3 using our number of moles and direction for each step. So to get our equilibrium constant, we're going to do a fraction. The top of our fraction is going to include any steps that are in the forwards direction. So that's going to be steps 2 and 3. So their equilibrium constants are 0.0689 for reaction 2. We're going to multiply that by the equilibrium constant for reaction 3, which is 0.0835. And this is where I got those numbers from for step 2 and 3. However, we also need to use the number of moles required as the power on those. So we're going to have 0.0689 to the power of 1. But remember, to the power of 1 is just the same as the number itself, so we don't need to include the 1 there. For step 3, we've got 6 moles of that, so it's going to be 0.0835 to the power of 6. On the bottom of our fraction, we're going to have the equilibrium constant for any steps that are backwards. So that's going to be reaction 1. Our equilibrium constant is going to be on the bottom, so that's 0.00185. And this is where we got that from. And this one is 3 moles, so it's going to be to the power of 3 there. So if we put that all into our calculator, that gets as an equilibrium constant of 3.69. So we can test that in this box here. Awesome. Okay. Finally, our products or reactants favored equilibrium. Since the equilibrium constant is greater than 1, that tells us our products are favored equilibrium. So as you can see, this skill is pretty much exactly the same as the previous skill. The only difference is we have some extra steps that we need to include. We're going to follow exactly the same method. So it's identifying our reactants and products in our goal reaction, seeing where those appear in our step reactions to help us decide the direction that we need. Then we need to figure out how many moles of each step reaction do we need so that they add up to give us that goal reaction. Once we've figured out the moles and direction required for each step, we can combine the equilibrium constants for those steps to calculate the overall equilibrium constant of the goal reaction. Any reaction steps that are in the forwards direction, those equilibrium constants are going to be the top of our fraction. Any reaction steps that are backwards, those equilibrium constants are going to be on the bottom of our reaction. Those equilibrium constants also need to be to the power of the number of moles required for each of those reactions.